right, let me try to get this hover cam to work because for some reason it's not working. Let's try this. Huh. This is not good.
I can come by, Mr. Hosman.
Well, the hover cam won't like connect to the actual camera on the hover cam. It's connecting to my like computer's camera. So I don't know why it's doing that.
So it's connecting.
Yeah, here, let me.
Why don't you try just restarting, and I'll talk to them.
All right, yeah, give me like 2 seconds.
Okay, do what you got to do. That Mr. Hosman, what's his deal? What's up, you guys? How are you? What's up? What do you guys got going on this weekend? Chilling? Yeah, I know.
My family's picking up my brother from college.
Jerome.
Yep, Jerome himself coming back home.
Tell Jerry I said hi.
Yeah, sounds good.
Today's actually Mr. Hosman's like last day of in person, and then you guys will be seeing a lot more of me real soon. Pretty much starting Monday. All right, so we'll be back together again, and hopefully he's getting a job at Bradley so we can get him out of my hair. So what else is going on? Chloe, what you been up to? I haven't talked to you in a while.
Nothing too much. How's your life?
You know, making the most of it. It's not very exciting, I'll tell you that.
Oh.
But you know, every day is a blessing. What are you guys doing anything for Thanksgiving? Are you laying low? What are you doing? Anybody? Low, laying low, I know. Did you guys buy your calculus gear yet? Hit up your family members. Come on, Gavin. You can scrape together $11 for a t-shirt.
I mentioned it. I forgot to send it to my mom.
Oh, tell your Uncle Dave. Your Uncle Dave played the NFL.
Buy me everything, yeah.
Has anyone topped my purchase?
No. Casey's gonna have the most calculus gear. He's gonna be chilling in his calculus jumpsuit and baseball hat. It's gonna be good. That's open until the 30th, so no obligation, but you know, you're gonna be feeling jealous when everybody else is walking around looking like a big nerd and you're not. Yeah, so no, today in class, all you're gonna do is a couple like linearization problems. So you made it through related rates, right? Related rates is always tough, and we'll keep working on that.
Okay. Come on. All right, can you guys hear me now? How about now? Can we hear me now? Yep. All right, cool. Sorry about that. My computer's being a little slow right now because I just restarted it, so give it a minute. Trying to present. So pretty much what we're doing today, you guys did awesome with all the related rates stuff we've been going through. And we know it was pretty kind of a difficult concept, but you guys did fantastic. And today we're going to be starting the next section of it. We're going to be doing approximating values of a function using local linearity and words are hard sometimes, right? Linearization. There you go. Got it. All right, but if you guys want to go ahead and take out your skill builders. Important thing before we actually get started, Delta Math is due Wednesday the 2nd. So if you got some time over the weekend after you watch that ed puzzle, make sure you get a couple of problems done. Right? Everyone loves doing math over the weekend, so I know you guys are going to have no problem getting some work done, right? But if you want to go ahead and take your skill builders out, we are going to be going through this section 4.6. All right, so hopefully you guys watched the ed puzzle last night. Mr. Shane did a great job explaining everything. And if you didn't, just as a little recap, right, local linearity and linearization, right, what that means is if we have, one sec. Oh, no problem. All right, if we have a graph, right, what we can do in really any graph, like let's take this graph for instance, x squared minus 6x plus 12, so x squared minus 6x plus 12. Right? What we're going to do is we're going to make an approximation for a value by kind of zooming in on that point or a point near it. And what happens when you zoom in, right? The closer and closer we get to a specific point, we start to see that instead of having this really dramatic curve, right, if we keep zooming in, right, we can kind of notice that instead of curving, it's starting to get more linear, right? Oops, sorry. And we can keep zooming and keep zooming. And the farther and farther we zoom in, we notice that it gets more like a straight line. So what we can do is we can take the equation of a tangent line at a specific point and use it to approximate values near that point. Right, so for instance, we have this equation here, right? The x squared minus 6x plus 12. And we're looking at the point x equals 2. Right, what we can do is use the tangent line, equation of a tangent line at this point to approximate the value at 2.5. Right, because it's pretty close. So when we kind of make that tangent line, right, we can kind of make the assumption that it's close enough to that tangent line that we can use the equation of the tangent line to find the value. All right, so when you think about finding an equation of a tangent line, which is something we've done a lot, right? Remember, it's using that equation that y minus y1 is equal to the slope times x minus x1. Right? And we have to find this x1 and y1. And then when we think about it, right, slope, another word for slope is what? If we're trying to find the slope, it's like we're trying to find the derivative. Good, right? So what we can do is first off, right, if we're finding if we're looking at the x value when x equals 2, right, that's going to be my x1. Right, the y1 would be the function value when x is equal to 2. Right, so if x is equal to 2, right, I want to know what is f of 2. Right, so that's just going to be 2 squared minus 6 times 2 plus 12. Right, which 6 times 2 is 12, so this negative 12 plus 12, that just cancels out, right? And it just leaves us with 4. So the x1 ends up being 2, the y1 ends up being 4, which just leaves us with finding the slope, right? Which is really, like we said earlier, just saying what is the derivative evaluated at 2. But before we evaluate it, we need to know what is the derivative, right? So quick power rule check. What is the derivative of f of x? Who wants to help me out here? 2x minus 6. Good job. right? 2x minus 6. Right, so knowing that this is the equation for a derivative, I want to know what is the derivative evaluated at 2, right? Because that's, again, that's the slope of the tangent line when x is equal to 2. Right, so this becomes 2 times 2 minus 6, which is just negative 2. Right, so let's just recap what we have so far. X1 is 2, y1 is 4, and then our slope, m, is negative 2. All right, so from these, we can plug them into our point slope equation to find out the equation of that tangent line. All right, so we just get y minus 4 is equal to negative 2 times x minus 2. All right, and we can solve for y, and we can write it like this: 4 minus 2 times x minus 2. Right, and if you watch the video, right, what this is this is the linear approximation. Right, so we can, there's a couple different ways we can write this, right, a couple different notations. One you're going to commonly see, right, is calling this L of x. Right, calling this L of x. Right, that's the linearity of the function at x equals 2. And why is this important? Right, this equation is what we're going to use to find the approximation of f of 2.5. Right, so really, L of x here, when we're finding it for 2.5, that's really like saying f of 2.5 is about, right, and then we just have to plug in that 2.5 into our equation here. Right, so we get 4 minus 2 times 2.5 minus 2. Right, which ends up being, when we solve it all out, right, 2.5 minus 2, that's just 1/2. Right, times 2, 2 times 1/2 is just 1. Right, so this is really 4 minus 1. We end up getting 3, which is our answer. All right, so what did we do? We took our equation, right, and this is that curve that we saw earlier. Right, let me just pull it up real quick. Right, and we found the slope of the tangent line. So really what we can do, if we take this equation right here and we plug it into our calculator, right, so this is 4 minus 2 times x minus 2. Right, this should pull up an equation of a tangent line, which is exactly what we have, right? Specifically when at x equals 2. Right, and what we're doing is we're using this tangent line, using the equation of it, to approximate the value of the function at 2.5. Right, so the question is, and you might have heard Mr. Shane talking about this in the video last night, right? When we're talking about these local linearities, we have to know, is this going to be an overestimate or is it going to be an underestimate? Does anyone remember how we kind of figured that out? Anyone remember? How do we know if it's going to be an overestimate versus if it's going to be an underestimate? Gavin?
So whether it's positive or negative, right? Maybe? No?
Not
Perhaps?
necessarily.
All
It,
right.
it's all right. Good job. It's more of if the curve of the graph, right, is it opening upwards or is it opening downwards? Because if you look at this, um, this graph is really above the tangent line, right? So if you think about the point 2.5, right, on this graph, it's really going to be above the tangent line. And if the actual point is above the tangent line, then when we use this approximation, it's actually going to be an under estimate, because the tangent line is under the actual graph. Right? It's got a lower value. It's an underestimate. It would be the opposite if it opened downward, right? If we had a graph that opened downward, then the tangent line would be above the graph. So it would be an overestimate. Right? Any questions on that? Any questions? All right, cool. Let's keep going. Let's look at number 3 here. We're gonna skip 2 for now and come back to it if we got time at the end. But number 3, we have a sine function, right? And we're gonna be using the same process here, right? So we know our theta, right? This is our x1. Theta equals 0. And we need to know, okay, well, if that's our x1, right, in that equation, the point slope form, what is our y1 going to be? And to do that, just like we did before, I want to know what the function is when we plug in that theta equals 0, right? So we get sine of 0, right? And who remembers, what is the sine of 0? What is the sine of 0?
0.
Yeah, it's just 0, right? Because if we look at our unit circle, right, sine of 0, that's looking at this point right here, right? It's the y value at this point, and the y value at that point would just be 0. Right, so our input to the function is 0, our output is 0, which actually makes our equation of the tangent line really easy. But first, before we get to that, right, we're going to need to find the slope, right? Which we know slope, another word for slope is just derivative, right? So we need to know what is f prime of theta, right? So what is the derivative of sine? Who remembers? Derivative of sine is what? Cosine. Good. Right, cosine. So if I want to know the slope when theta is equal to 0, I would just plug that in, right? F prime of 0 is cosine of 0. Well, what's cosine of 0? Yeah, it's just 1. It's just 1. So then our equation of the tangent line, right, that's just that y minus y1, so y minus 0 is equal to the slope, which is 1, times x minus 0. Right, which when we simplify this all out, it really is just y equals x. All right, so what does this mean? This means our local linearity, right, the linearization, that L of x, right, is really just x. It's just a straight line. All right, so we can use this equation and plug in what we're evaluating it at, right? This 0.2. So L of 0.2, which is just about, right, the same thing here, sine of 0.2 is, right, if we were to plug 0.2 in here, we would just get 0.2. Which is our answer. Now the question is this an overestimate or an underestimate? What do you guys think? Do you guys remember what a sine graph looks like? Yeah, Isaac was kind of drawing it, right? It's a sine wave, right? And I'll kind of quickly draw it for you guys here. Right, it starts at the origin and it just kind of keeps oscillating back and forth, right? So if you think about the point 0.2, right, it's probably going to be like somewhere around here, right? So what do you think? Is this going to be an overestimate or an underestimate? Why would it be under? Now, the tangent line, and I'll kind of draw it here real quick, would probably look something like this, right? Which really, if you think about it, the tangent line is over the actual graph, right? So this would technically be an overestimate. Overestimate. Because the tangent line, right, what we're using to evaluate the point is over the actual point, right? So it's an overestimate. Any questions on that? Overestimate. All right, so let's do one more. Let's go back to number 2 here. All right, so number 2 is a good one, right? Because it kind of goes back to our derivative rules that we might have gotten a little rusty on. All right, so we get to shake off the dust a little bit. So the good news is the beginning is the same, right? We need to find x1 and y1, right? Because the goal is to get to this equation of the tangent line, right? So our x1 is given there, right? It's just 3. Our y1 is going to be the function evaluated at 3. All right, so that would just be 3 times 3 minus 2 all over 2 times 3 plus 1. All right, 3 times 3 is 9, minus 2 is 7. And then 2 times 3 is 6, plus 1 is 7. So we end up with just 1, right? So next we know we have to find our slope, right? So we're looking for f prime of x. And we can tell just by looking at it, right? This is a quotient, so we're going to have to use our quotient rule. So why don't we do this? Let's take a second, and I want you guys to take the derivative of this on your own, and then we'll compare answers after we give it a minute. All right, who remembers our saying, like our little, how we remember the quotient rule?
Low D high minus high D low over the square of what's below.
Yeah, right. Low D high minus high D low all over the square of what's below. Right, so right away we know we're going to have something over this 2x plus 1 squared. Right, so then we just got to go through that little saying step by step, right? Low D high, we take the denominator, the low, 2x plus 1, times D high, the derivative of the numerator, right? Which just ends up being 3, right? Because we have 3x minus 2, the derivative of that is just 3. Minus high, so it's that 3x minus 2, D low, and the derivative of 2x plus 1, using the power rule, we all know that it's just 2. Right, so really taking the derivative isn't that bad. Now we just got to clean it up a little bit. All right, so we'll say 2x plus 1 times 3. Really, that's like 6x plus 3 minus, all right, we distribute this 2 in here. 2 times 3x is 6x, and then plus 2 times 2 is 4. Right, and that's all over 2x plus 1 squared. Right, so these 6x's, they're going to cancel out. We end up getting 7 over 2x plus 1 squared. All right, so we get my equation for a derivative. Now we just have to plug in our x value to find the slope at that point. All right, so we have f prime of 3 is equal to 7 over 2 times 3 plus 1 squared. All right, 2 times 3 is 6, plus 1 is 7. All right, so 7 squared, 7 over 7 squared is really just 1 over 7, right? Because the 7 on top is going to cancel out with one of the 7s on bottom. So we just get 1/7 as our slope. All right, so plugging that into our point slope form equation, right, we got y minus y1 is 1 is equal to the slope 1/7 times x minus 3. Right, which we can solve this for y. Right, we get y is equal to 1 plus 1/7 x minus 3. Right, then we just got to plug in the value we're looking for, right? This 2.9. So we know the L of x, right? Which is really, I should have put 2.9 here, right? Because that's what we're evaluating at. 2.9 is roughly 1 plus 1/7 times x minus 3, which is, sorry, I don't know why I keep writing x. This should be 2.9 minus 3, which we could just kind of punch that into our calculator, right? We get 1 plus 1/7 times 2.9 minus 3. And we end up getting and we'll round this out a bit, 0.986. Right, so now we got to think, okay, is it going to be an overestimate or an underestimate? And for this one, it's definitely a good idea to graph it so we can kind of see what we're looking at, right? Because we got 3x minus 2 and 2x plus 1. If we graph this, remember we're looking at 2.9, which is somewhere here, right? Are we going to have an overestimate or an underestimate? An overestimate. Do we know why? Yeah, right. The tangent line, the tangent line is going to be over the graph at 2.9, right? So we have an overestimate. So I'll just say over. Any questions on that? No. Any questions from you guys at home? All right. If you have questions, feel free to hang out. But that's all we have for today. We got about 5 minutes left, so we'll kind of call it there. You guys did awesome today. Great job. And if you, like I said, if you have questions, feel free to hang out. But if not, you guys are free to go.
Have a good weekend.